Hello. So let's dive right into the topic. We are talking about web handling, modeling, and simulation with MapleSim. So I have a few slides prepared, and then we will also go into the tool and look at some models and simulation results together. So in this session, we will talking about let's talk about the scope. The type of models that we're going to be focusing on would be machine direction models with one-directional flow. MapleSim is a multi-domain, a causal system-level simulation environment. And so web handling simulations within this environment also involve system dynamics. The web handling is a library of components, and we will see and get to know those components and how they can be used to capture roll-to-roll processes. They work with other libraries in MapleSim and allow you to create models and capture various dynamics. It has a simplified design, and we will see shortly. Includes all the basic components that you want to include in a roll-to-roll process. And it has some extra features that we will review. As I said, MapleSim is a multi-domain modeling and simulation environment, and it comes with different libraries for different domains. The latest addition to MapleSim is the web handling library. So let's take a look at what's inside this library. Obviously, the starting point would be the web material. We'll look at the content of this record that captures the web properties a bit later. Probably the most important would be the web span. This is the component that goes from roller to roller. We have different types of rollers, nips, and either pole rollers with different level of detail. We cover the source and sink or start and end of a roll-to-roll process. The wind and unwind drums take care of the variation in inertia and also the variation in the radius. Some additional components to help put things together. There's a load sensor to kind of emulate what one goes through building a tension sensor in a web line. This is simulation, so we actually have the values for tension everywhere. But if you want to emulate a load cell, we can do that with the components in the library as well. And some other pieces or primitives that allows us to these components allow us to hold things in place, move things around, and create a dynamic model. So let's spend maybe a very little amount of time in the foundation of the library. It's very important to make sure that we know that this library that we're going to be looking into and using to answer engineering question is standing on solid ground. So the basic approach to capturing the web dynamics would be to designate a control volume for our web span. Control volume is defined by the incoming tension and outgoing tension, the velocity of material or the web coming in and the velocity going out. And with those values that we know, the main law that we are going to be using, and it's used everywhere, is the conservation of mass, which basically is nothing but saying that the mass coming in, if we subtract the mass going out, whatever is left is the rate of change of the mass inside the span. This equation can be manipulated to become something that we want to simulate. In a lot of cases, this manipulation it gets continued to a overly simplified form by others, or even they throw away all the time-dependent parts to it and make it static or quasi-static. We won't be doing that. So we will solve the equation in its most general form that relates a strain in the web to its velocity and also tension to a strain. So we put that together, that becomes the basis of the span formulation in the web handling library. I mentioned the web properties block that would capture the web and would define the web. So we have the width, we have the thickness, density, modulus of elasticity, Poisson ratio, and a few other settings for simulation and visualization. Now that we have the web figured out, let's see how we would go about and build a library in MapleSim using the web handling library. We will look at the tool a little bit later, but for now, as an introduction, I thought it would be instructive to build a model basically together. So let's say this is the system that we want to analyze. It's a rotational dancer. We only are focusing on a portion of the web line. We have the upstream boundary conditions, the tension and the velocity, and downstream boundary conditions. So we only look at these 4 idler rollers and the arm in the middle that is spring-loaded and would react to the tension in the line. So the first thing would be to define the boundary conditions. So there's components for that, a source and a sink. So we'll need those 2. Then we would need rollers. As I said, there are 4 rollers here. So there's a roller component that one would drag. And this slide is also similar to our canvas in our modeling tool, MapleSim. So each of these rollers, you have the option to say the web goes below or above. So you can quickly arrange the model as you would require. The next step would be to kind of bring the web spans so that we can later on connect everything together and create one stream of material flowing through our model. We need to hold things down that are not moving. So we use a fixed frame and connect the rollers, the 2 fixed idler rollers, and also use them to fix the point where the web enters our model and where the web exits our model. So we have all of those. Now the 2 rollers in the middle, they're not fixed. They actually rotate with respect to a pivot point. So there's a component for that as well. So there's a revolute joint and a fixed point. So that takes care of the pivot point. And then we need the arms. So we use an option on the roller component to extend an arm up and down with parameters that are available in the component. And now we have everything that we need. So we just need to connect everything up like this. So now we have a model. There's some other pieces that got added, namely on the left-hand side, you see here on the source, we are using signals. One goes to tension, the other one goes to velocity. For this simulation, we are assuming the upstream tension and velocity are constant. If that's not the case, we obviously can use different types of signals. Similar to what you see on the downstream side, on the other end of this model, we have a sink component. And for that, we are specifying tension. We actually, with that, as the shape of that icon shows, it's a ramp. So we are gradually increasing the tension of the downstream. And you can see that effect of that tension increase in the rotation of the dancer arm, because that dancer arm is under spring load. This potentially can be used in a variety of scenarios, like feedback for tension regulation. I will see an example of that with a different type of dancer a little bit later on. So just to finish this example, we have the model. You can see that the arrangement of icon in an actual model is one stream. So with the help of parameter values, we tell MapleSim where everything is. We don't need to actually put them relative to our layout. Now we want to add 2 more idlers to add a little bit of accumulation or storage in this dancer as we have it like this. So if we look at it, and follow the web, we can kind of find out that these 2 new rollers have to sit in the middle of these 2 rollers here. So with that, we can just add the additional pieces. They're fixed rollers, so we have a roller and a fixed frame. And by just adding that, we can expand our model and take a look at it for a different purpose. This is one of the features that I wanted to highlight, as in with this approach of block diagram, you can quickly investigate what if scenarios, as in what if I had 2 more rollers, what would happen, and things like that. There are a lot more parameters, engineering parameters that you have access to. We will review some of that, but the basic things that you would imagine for interaction of web and rollers are captured, such as inertia, diameters, inner diameter, friction, things like that. So they're all parameters that you can access and specify to capture your roll-to-roll process. Okay. So at this point, we will jump to MapleSim and take a look at some examples. The examples give you a cross-section of things that you can do. You can do a bit more investigation into slippage. We can emulate a load cell, as I mentioned, and try to mimic a real scenario instead of using MapleSim's true values of simulation for the tension. We can estimate the tension as we would in a real world and try to complete the model that way. Or we can look into more details type of web roller interaction. We will look at the extension of models with some controllers to do speed control or tension control, and a very, very quick example of how to deal with resonances, or actually identify resonances from the system parameters. We're actually going to start with a bit more complicated model, and that's an accumulator. We'll see this model in MapleSim. This animation that you see here is the model that is kind of the process is built into it, that we turn off the rewind roll and let the accumulator pick up the material, and then we restart the rewind roll. Think about abstracting a process that is going to happen, like the changing of the roll. And then we do the same thing on the other end by turning off the unwind roll and let the accumulator provide the material for the process. You can see with the color coding that is based on the tension variation in the system, we have included in this model some losses in the bearings for the rollers. That's why we have this gradual change in the tension from the start to the end of the accumulator. So the process of ramping up, turning on the system, turning off the system, those are all can be captured as the system includes all the dynamics, like the inertia loads from the rollers and the slippage. So let's just start actually from this model. There's a little bit more that we need to come back to this slides at a later time. So I'm going to go in here. So this is how that model is going to look like. I'm going to turn off this panel to just focus on the canvas first. So you can see that compared to the model that we built together a moment ago, this has more rollers. So you can have as many rollers as you want to capture the system. Similar to the arms for that pivot, we have components or the rollers that have offset activated. As you can see, in a typical roller component, we have the inner diameter, the outer diameter, inner diameter length, and we can have MapleSim estimate the inertia for the roll based on its density, or we can not use the approximation or estimate and provide the exact inertia from our actual design. We can decide to include a simulation of a slippage in the model or not. Even if we don't include the slippage, which we can still use the simulation to see which of the rollers were at risk of slippage. We'll look at the results one more time and look at some additional results for this model in a minute. You can see that we are using a unwind on one side and a wind roll on the other side. Both of them have torque applied to them to create tension. This is ideal torque that could represent a brake or some sort of an actuated or active system that would can be deployed to regulate the tension in the span. The accumulator is actuated by a very simple scheme in this model. Obviously, this could be a starting point for a model, and we can add more detail into the model. So it basically looks at the wind and unwind speed, not the actual rotation, but the speed is measured at the nips on either end, and that value is used to control the speed of the and direction of the accumulator. So let's go back to the results for a second. So we have already seen the animation, and I'm going to play the animation. But on top of that, we can look at some plots for the system. So here I have a number of plots for this model, and I can have as many as I want. But the point here is that I might be focusing on certain aspects of the model. For example, here you see that I am probing the tension as the web enters the accumulator, and also as the web exits the accumulator. I'm also just to demonstrate the capability in the library, even without simulating the aftermaths of the web slipping on a roll, I can find out if there is a risk. So I'm probing on this roll, instead of speed or torque or anything like that, I'm probing the limit. Did it reach the capstan limit for potentially slipping? And if I zoom in, I can see that during the half a second start up phase, I actually had that roller switch from 0 to 1, meaning that it has crossed the threshold, the capstan threshold, and it could be slipping. If you want to look at what happens if a roll actually slips, then we can activate that feature and take a look at that. So let's just do that. For that, I am going to pick up one of the examples that comes with the library, and that is the disturbance propagation. Here it's hopefully a typical one, but it's a fictional setup here to demonstrate the process. We have a series of 4 pull rolls with the assumption that the last one, I'm going to simulate this when I'm describing it. The last one has some sort of an error. It's a sinusoidal error. So it's going with a velocity, but there's a fluctuation of velocity on top of that. And the one before that, on the upstream side of it, has a slippage enabled. You see that this checkbox is turned on, which means that I'm not just wanting to see whether I hit the threshold or not. I want to actually see what happens. And in this case, we know that if the roller slips, there is upstream propagation of a tension disturbance, and we won't just exactly see that. So we know that this span is going to have tension fluctuation because of the error in this motor, but because of a slippage here, we're going to see the tension fluctuation in the upstream or the span before it. And this is what we are looking at here. You see this tension plot that I have, because I have, if I zoom in quickly, I've activated a sensor on this web, and I am asking MapleSim to give me the plot for the tension in this span, which is what I have here. So I can see that, and if I play back, so everything is fine, everything is ramping up, but at this point the fluctuation starts. This is the roller that has a faulty motor on it, and this is the roller that is slipping. And you can see that with the color code, you can also see that the tension definitely varies on the upstream side as well. So then at this point, although this is a hypothetical situation, there are real cases similar to this, that you would say, I want to increase the tension to see what happens. I want to change the roller position to deal with my deal with the wrap angle variation, or you can utilize another feature in the roller and add some suction and kind of with that vacuum see the effect of that on the simulation. So let's keep this original one and add the surface pressure. So let's say just put 30 here and re-simulate. So what I'm doing is I'm trying to see how I can play with the system settings to have a better design. And let MapleSim be my sandbox to test different ideas. So I have the first set here with unfortunate upstream tension fluctuations. Now I have added the suction on the roll, and it will take care of the wrap angle and all of that when calculating the boost to the friction. And now you will see that the new plot is red and the old one was green. And we definitely have much less fluctuation due to the boost in friction with the negative surface pressure. And if we just play back the new simulation, we will clearly see that although this span is suffering from fluctuation, the disturbance is not propagated, or at least not significantly, to upstream cases. So this was like a really focus on the roller. I have one more example, actually two more examples before I run out of time. So let me just open a case of tension control. So we already seen a dancer in this one, but this is a case that kind of showing off what else you can do under a dynamic simulation. You can put as many as rollers, dip rollers, and idler or pole rollers together, but you can use MapleSim's other features to kind of investigate different controller strategies as well. So I have, again, a dancer. I have a revolute joint with a spring. So you might have different types. You might have pneumatic cylinder to provide this resistance to balance out the mass in the roller and the arm as well. So some basic calculation, as you can see on the screen, are added right into the components. I have an encoder, an ideal encoder to give me the angle, some gain, the desired tension, and a PID that is activating an ideal brake to or an actuator to my unwind drum. And here's the situation, this being the target. I want it after the initial ramp up to keep the tension steady, although I am losing, like the material is being removed from the unwind roll. So it becomes has less inertia as time passes. And also it loses radius, as you can see in this plot of the radius of the roll. And this is the tension that is being applied, the brake tension that is being applied to the drum to keep the tension steady. This would be the place to investigate this type of scenarios and kind of play with it and come up with the best matching your intended function. One last piece for this session today would be to give you guys a sneak peek into what comes next. The new version of the library is coming out with the new version of MapleSim pretty soon. So I felt like should give you the main part of this new addition to the library, which is a new sub palette for the library called Laminating. This addition to the library would allow the user to easily have a roll-to-roll process that has multiple webs. Here we have 3 branches, 3 unwind rolls, as you can see here. They come into this laminating or merge section, and they turn into one. And so this is branch 1, branch 2, branch 3, 3 different web properties. And if you want, you can use a built-in law of mixture web property for the merge, or you can say, I want to specify exactly what I want. So you cannot use this merge web properties and specify the properties of the laminated web yourself. So let's take a look at what it looks like. So here is intentionally use different colors for different lines that come together so that it's clearly visible. Obviously, one of the main pieces that in the laminating process one would want to be aware of it would be the strain in on the incoming lines. So just like tension and velocity, you can measure strain as well. As you can see in the top plot here, the tensions already have played with a bit for this model, such that we get identical strain for the 3 lines that come in. So you can imagine with the tension control and all the other features, you would be able to investigate how a laminating process would work and put it under different conditions, dynamically, a start-stop, different speed, different material properties, and easily rerun the simulation so that you can investigate this type of work. So the only other thing that I wanted to include in here is that once we create these models in MapleSim, some other one main use case other than just investigating and designing would be to do virtual commissioning. So for that, we can export our models in a variety of different ways so that you can use your automation tool to have it interact with your PLC program and make sure that your controller is doing what it's supposed to do. One of those things that you can do with this, one of the ways of export would be to export a model as an FMU. To go back to the original accumulator, here instead of using an automation software and PLC, I'm just going to run that FMU to give you an idea of how would that go. So here I have the compiled version of my model. We are not in MapleSim anymore. We are in a tool called MapleSim Insight. And here I can run the model and interact with it. So I am acting as the controller here. And for example, I can at this point turn the exit or the rewind drum off. So it will stop, as you can see here. And because the logic is implemented in the model, the accumulator is picking up the slack. So I can turn it back to normal and then do the same thing for the other side. And all the while that I'm doing this, I can monitor the tensions and see if the model is behaving as I want at the same time that I am testing my controller.